So can you see my presentation?
Yes, I see it.
Okay, that's good. Yes, so we will talk about parallel computing with Python, and we will learn some concepts into these parallelization schemes. So what I will do today is just a demonstration, right? So let me activate my camera. So so it's not recommended right now to type alone because some of these commands require time, right? And also for the compilation. So in the recordings, you can take a look at what happened with the commands, right? And then you can follow that workflow. But right now, I will do so use a demonstration. Or you are very fast, right? So you can go together with me. So these are some requirements, yes, that you need to follow before you can run the examples below. Yeah. So in particular, for instance, here we need these packages for Python. So this is the Python version that I will use. And the requirement for this Python version is this GCC core module, right? So what I can do is that I can go to this window. Let me close this. Go to this one, and then I paste the requirements, right? And then I create a virtual environment, as Birgitte mentioned before. And here you type the virtual environment, and this is the path to your environment that is, in this case, in this particular case, is called VPYN Python course. But you can name it as you want. And yes, it could be more related to what you are doing in your project. So you type virtual environment. Yes, here is the name of your environment. Here, this is the path where I will put my environment. And this is the name of my environment. It's a Python course, right? So it takes some time to execute, yes, and that's why I executed that previously. And then you will see that the virtual environment with this name was created, right? So this is the command you should follow, and then also you need to write the path to your environment. So in my case, the environment is located here in my directory, my current directory, and it's called Python course. So this is something that you need to do first. So now once this environment folder is created, so you need to activate that. And you can do it with the source command that was also mentioned previously. And then you type the path to your environment and the name of the environment, which in this case is just Python and a course. Oh, sorry, it's a course, and then is the bin and the activate. So this is not only the folder as I did before, but it's just bin and then activate. So now it should be activated. So then after this, you need to install the Numba, which you require for one of the examples. And you can do it with the command shown here, right? So I can paste it. I copied the command here with this button and paste it directly. So as you can see here, it takes some time to install, but in this case, it was not that slow because I cheated a little bit and I installed it before. Otherwise, it takes a time to install the packages. Here for this MPI for Pi example, you also need to install MPI for Pi. So I will copy this command, which is the requirement for this MPI for Pi. Yes. Now I just copy and paste the part for Pi MPI for Pi, which will enable MPI in Python. So also this takes some time, and because of that, I installed that previously, and you can see here that the requirement is already satisfied because I had already MPI for Pi in my environment. So the next thing that we need to install is NumPy, because in this Python version, it is just the base or the most basic Python without many modules, right? Just like a lightweight Python. That's why you need to install the other dependencies like NumPy, MPI for Pi. But it's also convenient if you need some specific version of NumPy. You don't want to get into conflicts with existing installed NumPy versions, right? So here I install NumPy. Also takes time. I did it previously. And here, this is the requirement for one Julia and Python example. So first you need to load the Julia. Yeah. And then you install Julia with this command here. So it's also satisfied because I also did it previously. So now what you can do to activate Julia is to start a Python session, as I'm doing here. And then you import Julia, which is the module that you already installed here. Import Julia, and then execute this command here. So this will install the PyCall package and make the necessary adjustments to use Julia within Python. So just copy, paste it, yeah. So as you can see here, this module uses PyCall, and then so it fixes the paths and makes the consistent installation. After this, you can exit Python, and you should be ready to go. So the example that we will deal with today is just a 2D integration, and this is the integration over this range here for X and this one for Y. And the integral is for the function sinus of X plus Y. And this is a interesting example for us because once we know the exact solution, yes, so we know what we will get from the program. And also because it is time expensive, and because it includes two integrals, as you can see here. So one way to parallelize this code here, this function, or this integration, is by creating grids in the X and Y directions and divide the range in these two directions into n bins. Yeah. So this is a code without any optimization. As you can see here, it's a serial Python code. And here you can see the grid size, yes. And here we call this function integration to the serial. So we divide the entire range from 0 to pi into n bins. And this is a variable to accumulate the summation. So here we are performing the integration over n bins in the X range and also in the Y range here. And here we are collecting the sum, yes, in this partial summation. So finally, once we get the total summation, we need to multiply it by the bin size square, right? Because it's a square grid. Then next we have the main function, and we time the integration to this serial. And finally, we print out the error, right? We know the exact value, which is 0. So this will print out the error or the difference, yes, more precisely. And this is the time that is spent in the serial region, in the serial function, sorry. So yes, so once we have this function here, which is in serial mode, we can go to our script, as Birgitte and Bjorn mentioned before. So we have some script, yes, and here are our modules that we need, yes. This is an ML purge line to purge all the modules that you have loaded in your session, and it's convenient because otherwise there could be some conflicts with the modules that are loaded here in the batch script. So then I am requesting only for 4 cores or tasks per core. And here I am loading or sourcing the environment, yes. And this may change in your case if you have a different path. Yes, of course you will have a different because this is mine. And here I will uncomment first the integration to this serial. This is the one that I have here, right? And the way to submit this script is by using sbatch job.sh, as Birgitte mentioned previously. Then you get the job ID here. You can check how is your code doing. So you can see that it is running, right? It is running, and it shouldn't take a long time. So we can check here the output file and the error file. So if you have some errors, it will be printed out here. And also the output, if you printed out something in your code. Yeah? So we can see now that the output error, the output file is ready. So we can check what it contains. And you can see that the time was about 21 seconds. Yeah? And this is the difference that I mentioned before with respect to this exact solution. So it's doing well in the case of serial code. But remember, this is a very simple case. And already with this case, we can see performance improvement when you move to parallel algorithms or parallel scheme. So very important, if you want to get the same timing, it's very difficult, right? So because it depends on how busy is the node and some tasks that may be running in the background. So it causes some differences in this, and that's why when you are timing the code, you should repeat it several times to get good statistics. So first, when you want to parallelize your code, so the first thing that you need to identify is what part of the code is most expensive. Already, for instance, in this case, we have some parts of the code. This is the initialization, so not that time consuming. This is also an initialization, which is not time consuming. But here there is a bottleneck, right, in this double loop, because here is what is consuming the most of the CPU time. And this one, which is just writing the final solution, collecting the final solution, is also not that expensive. So you're already in this simple code, we can identify which are the most expensive parts, and in this case is the double loop. So there are several optimizations that we can do. The Python already has several options to make your code faster without investing a lot of time, right? And one of them is the Numba module, which provides you with some decorators, the so-called decorators. And here is the serial example that I mentioned before with the Numba decorator. Notice here that I have also the serial function again, but this time we will use some Numba decorator, so everything is the same. So I didn't change anything in this function. This was the same as before. But now what I can do is that I can use the ngit function from Numba. So this will allow me to pre-compile and get some machine quality code for the same function is in the serial mode. So that's why we installed a Numba previously, and then we can run this. I have it already in my script, but it was commented out. So now I can uncomment it. So this is the serial mode, and this is the example in serial mode, but with Numba decorator. So I will run it. Check the job, and now it is running. This is the job ID. But the part that takes time is the one for the serial mode without, yes, without the decorator. But now let's take a look at the output. And you see that for the first part, it took 21 seconds. And let me see. And for the Numba example, it took 3.9 seconds. So this is a good performance. So notice again that this time would depend on strongly on the run, and then you should take some average. Yeah. Yes, yes. Before going also to some parallel protocol or paradigm, so there are also other alternatives that you can take. Yes, before going into the parallel ship. And another one is that we can use low-level programming languages such as Fortran, C++, to make the difficult parts or the most expensive parts faster in Python. So here I use Fortran, but you can also do that with C and C++. So this is the part for Fortran. If you remember, this is the integration to the function, but now it is written in Fortran. So you can see that there are some similarities, the variable declaration, and this is the expensive part, which is the loop, right? So then we multiply by the grid size. So then we need to compile. This is the issue with this type of a scheme, that we need to compile the Fortran or C code. And this can be tedious if you are doing that under the development phase, right? When you're doing that many times until your code runs. But otherwise, it should be faster if you already have a production code. So now how to compile the function? You use the fupy command, and then you compile the Fortran function with this, yeah? So once you install the NumPy, so this command should be available. Now notice that the function is compiled as you would do it in a standard Fortran code or C code. And then this Python API is CPython API is created, right? So then you can use this inside a Python code. So this is a Python code for calling a Fortran script, right? So you can copy this and paste it on your terminal. So I copied that, and I have already it in my directory. So I call it Fortran, and you can see that this is exactly the same, right? Or it's the same code. So here, this is the Python code, yes, and here you are importing the function that you generated, the ISO image, and then you will use that in your code here. So this is the way to call the function. So now we can go to our script. And here I will comment out this one, and just call the Python code. Sorry, the Fortran code. So then I submit it. So it's running, and the output is here. And you can see that the time now is 1 second. So for the initial code, it was 21 seconds, right? So now the time is reduced when you go to a lower level language. So what we saw that for Fortran and also for C++, one is to compile the code every time one changes that. And another alternative in Python is that one can use Julia, which doesn't require a compilation, and it follows a similar scheme or paradigm as Python, where you can dynamically type your code and get the result. So this is a code that I wrote for the integration to D, but this is now in Julia, right? So you don't need to compile this, but you need to do the settings that I did at the beginning, yes, for the requirements. And once you have this code for Julia, right, you can write your Julia code for expensive parts in your code. So then you can create a caller similar to what we did with Fortran. So in this case, we import the Julia module, and then import main. This is a function from Julia, or a method from Julia. So here we execute our Julia script, right? And then from here, we can call our Julia function or integration to D, but now in Julia. So we can execute this with the Python code Julia. Now we will comment out this Fortran. I will call this one. So this is Python now for Julia. And let's see if it is working. So interesting. This part is not working, but I can fix that. Let me see. Call Julia. So here I will need to do this is Julia install, right? Within the Python, within the Python caller for Julia. And see. So it's running. Interesting. It's taking some time. Okay, so there should be some issues with my environment. And well, I will show you this on the command line, right? So here, if one, so I notice this, if one is working in a Python environment, yes, one needs to fix the paths, right, that the Julia caller is using. But if I am here on the terminal, let me see.
So this is the Julia side, right?
Yes, that's correct. Yes. So, but now, yes, well, one needs to fix the paths where one is working in an environment, and once we fix this, you can see that it runs and it takes about the same time that the Fortran code. So, but if you want to try this scheme and you get into this type of issues, just let us know. It's now I think I know what's happening. One needs to fix the paths properly.
Yeah. On UPPMAX, I think PyCall is already there, and maybe pre-compile as well. Yeah, you will notice.
Okay. So yes, now we go into the parallelization schemes, right? And the first one is with the threaded scheme, right? So here you will work with the workers or threads, right? And they share some memory. So a good thing here is that you don't need to install anything because the threading module is built into the Python base library, so you don't have to install it, right? So, but unfortunately, for compute-intensive task, as the one that I did before with the computation of the integral, so you won't see a performance improvement, right? And this is because Python has an internal mechanism called the GIL, yes, which serializes the code. But for other tasks, for instance, if you're writing and reading files, this could be useful, yeah, but not compute intensive. So this is some code that I wrote for the integration 2D with the threaded mechanism. And here you can see what is the difference. Now it's called integration 2D threading, right? So it's using 4 threads, 4 workers. So here you need to divide the workload by the number of threads, right? So then you set a lower and an upper integration limit for each thread. So the workload will be divided. So then you collect partial sums and then store the partial sums into this array, right? And yes, when it finishes this part for all the workers, so then the total summation is computed, right? So to generate the threads, you can use this threading thread function, and then it will create a pool of threads that can do the job for you. So how to run that? You can type Python, the name of the function, and it will run. So it will run because here you specify already the number of threads, and then these threads are created here, right? So this is one way, and as you can see here, this scheme is not efficient. It takes even longer than the serial case. And this is because of the GIL problem that I mentioned above, yeah? So there are other mechanisms in Python, and I will show you right now. So there is also some implicit threading if you're using linear algebra operations and linear algebra libraries, such as these ones, yeah? So internally, you can use the parallelization schemes from this library. And if you want to know what is the requirements of what is the settings for these libraries, you can take a look at the NumPy show config. So it will tell you what is the library and how to set, and then you can learn how to set the threading mechanism for that. So this is a trivial example. This is the dot products of a matrix. So here, this is a matrix of this size, yes? And then we perform the dot operation with the NumPy dot function, and we time this code, right? So the way to set the number of threads is by writing this, yes, on your batch script, if you want to use one thread, right? So then the Python and the name of your file, in this case is .py. So and it takes it 1.14 seconds. So if you want to use 2 threads, then you can set this to true, in your batch script, for instance, run the function and you will see performance improvement. Yeah. So we can use also a Fortran in a parallelized mode. In this case, I'm using OpenMP. It's also possible. We take the previous function for Fortran and we add an OpenMP parallelization layer here, right? So, and then the two loops are executed in parallel mode with OpenMP. So, but the issue is similar to what we saw before. We need to compile the Fortran function. And in this case, the Fortran function is called Fortran function OpenMP. So you will regenerate an OpenMP version for this. And once you have the ISO file, so you can then call this ISO file in a Python script, as I'm doing here. And then you can make use of the function that you define in that file, right? So integration and with OpenMP. So here you can set the number of threads in your batch script. And I'm setting this to 4. And you can see that the performance is improved. So from 21 seconds, it is reduced to 0.30 seconds. Yeah. So we saw already that for the threaded mechanism that is internal to Python, one cannot get a good improvement in performance. But Python has also other tools for parallelizing the code, and one of them is the so-called multiprocessing module. So in this case, we import multiprocessing. It also it's installed already in Python. So, and here we do something similar to what we did in the threaded mechanism. We set the number of processes. In multiprocessing, we call the workers processes. And then in the integration function, we divide the workload by the number of processes. And we set the limits for the integration in this part. We accumulate the partial summation from each worker into this array. And finally, here, we start the pool of processes with this function, multiprocessing process. And then we need to append them. And then here we start the computation. And here we join the processes so that we wait for all of them to finish. Once we have the result or the partial results, we accumulate all of them into the integral and we report this value here. So we can do that with four processes, and then we can see that the execution time is reduced from 21 seconds to around 6 seconds. So it was good in this case. So this is a more advanced example, yes, and it includes an MPI parallelization scheme. And in Python, it can be used with the MPI 4Pi module. Here, that's why we installed previously MPI 4Pi. So if you know already about MPI, you can see here the required settings for MPI, including the communicator, the size, and getting the ranks. Here we divide the work as we did with threading and multiprocessing before into all of the processes. And here we set the limits for the integration interval, collect the sums, right? Or the partial sums. And finally, we do a reduction operation to get the total summation, right? So if we use four MPI ranks in this case, so we will see that the performance is similar to multiprocessing. So we are getting some speed up here. So for MPI, so the script would look like this, the HPC2N. So these are the required modules. You need to activate the environment because we install MPI for Pi in our environment. And here is the way to run the Python script. API, the number of MPI ranks, in this case is 4. We should be equal to this one. And then the name of the script. This is the case for UPPMAX. And here you can see that the modules are different, right? You need to activate the environment, but the execution line for MPI is the same as in HPC2N. So monitoring resources, our tool at HPC2N, it's as mentioned here. So there is a command on the terminal that is called job usage. And if you type job usage and then the number that you get when you submit that script, like this one. So then you will get a URL. And once the job starts running, you will get this URL with the timings right here and the job information. So you can go and copy and paste this in your local browser. For instance, here in my local machine. And then here I can see some statistics, but it takes some time to see the statistics, like some minutes. So this is our tool that you can use to monitor if you're using, for instance, GPUs and you're using the CPUs in a proper way. So, okay, so I will go to a Dask a library. This is a library for in Python for parallel programming, and it is flexible, so it interacts or it can interact well with NumPy, Pandas, right? And also offers the possibility of doing some asynchronous computations. So in Dask, you don't execute the commands right away, but you just generate the graph. And just when you instruct Python to compute the graph, then it will perform all the operations. So how to work with this? This is the setting for HPC2N, because in this case, we need to use Jupyter notebooks in a computing node. So here is my folder on Kebnekaise. So you can get this notebook in the exercises folder in the GitHub. Yes, on the repository that you clone, there should be an exercises folder, and then you will see this Dask notebook. So this is here in my case, here, and then you should be able to use that. So for that, the HPC2N, we need this script, and I have already one in my session here. So these are the lines that you need for a Dask. These are the modules, right? And here we start the Jupyter lab. So, so the way to do this is by sending this job to the queue, and then we wait until it starts running. So it can take some time, I think, in this case. Interesting. So, well, this is the way to do this, and then once it start running, so you will see slearn script, right? Which is called something like slearn .sh. No, slearn output. Sorry, slearn output, and then in this slearn.output, you should copy and paste this line here. Well, a line is starting with this format, right? Copy the entire line, then go to a browser and open it, and then you will be able to use the notebook. But in this case, it will take time. So I will cancel this. And this should be done just for a very live well task, and that's why I won't run anything compute intensive on this node. But as it was mentioned before, so you can also run the Jupyter notebook, but here I will do it on my login node, but this is just a lightweight, I would say, and it's because otherwise we will wait a long time now. So this is the line that I mentioned that you need to copy. Yes. Once you get the job started in the queue, so just copy and paste this line, open your browser. Notice here that this browser is on Kebnekaise. So then just go and paste it. And you will see that Jupyter is here. And now, let me see. Close this one, close. So what here seems to be very small in size. Can you see the text here?
It is very small.
Okay. Let me see, increase. No. Oh, well, I will try this one. Good. I don't want this. How to close this one? Okay. So now, what about now? Maybe I can increase it a little bit more. Now you can see here is the notebook. Now here I'm using an example with pandas data frame. So first start the pandas, then here I am creating a large data frame, and this will be called large data frame .csv, and then I am timing the pandas reading function. Yes, it will read a CSV file, and then I compute some summation here. Yeah. Then I report the timings here and the result. So what if you use the Dask, then you should call this Dask data frame for a data frame, and this is the shortcut. So then you use the read SCB or CSV file function with this file here. Here you can specify a block size, yes, so that you divide the entire array into small chunks. And then here you perform the same computation as before, but now this will be done with Dask. So here you can see the same result as before, but the reading time is reduced. So this time can be reduced if you change here the size of the block that is read by each task. So by using this size and the total initial size of this file, you can see that there are 17 parts for the entire array, right? So so Dask uses several workers to make the computation, right? So in the case of NumPy, there is also a good integration. Here there is a relatively large data array. And here one computes the mean by using NumPy and takes the time. And here one report the result and the times. So, but in the case of Dask, there is also an option for Dask arrays. And here we use the array defined by NumPy, right, that we did before, and we divide that into 8 chunks, right? And if we do this, then we can do the computation, but now using the Dask mean function over the Dask array, yeah? So if we do this, we notice that the time is reduced from 0.16 to 0.02 seconds, and the result is the same. If you're curious, you can print out the Dask array, so the information, and you will see that 8 chunks of the data, this was the total data, yes, that we had in the array, and we created 8 chunks. And on each chunk, Dask will do a partial summation. So it's a nice feature in Python to deal with large array or data frames, and also to introduce parallelization to your code. So is there any questions at this point? I think I am over time. I will close this. But as I mentioned before, if you want to run this, the option to do it is by using the Slurm system. Yes.